So good morning, everyone, and thank you for attending this session about Dataiku Flow. So my name is Clément Stenac, and I am the CTO of Dataiku. Dataiku is a French startup founded this year. We are a software editor, and our goal is to make software that makes the life of data scientists easier and more productive, and to try to fix the pains that data scientists feel. And there are many pains for a data scientist. Some are related, for example, to handling data, basically just getting data in the system, so parsing all kinds of data formats, doing data cleansing, normalization, enrichment, going from raw data to stuff which is really usable for real data science, so basically doing some advanced reportings, doing some machine learning, etc. And one of the pains which is associated to that is handling data pipelines and data flow. For example, this is what could look like the data pipeline of an e-commerce company. So you have lots of silos with input data. So you have all the CRM data, all the web tracking, all the search engine data. So all of that in really different formats. And there are a lot of analysis that you want to perform to, in the end, get a few outputs. So a new product recommendation, some reports, some data for search engine optimization. And you have really a large number of stages. If we zoom just on one thing, which is a recommender here, just a recommender is actually first, you have to start with your tracking logs, the page views, your CRM orders and customers table, and you have to make at least a dozen stages just to go to one thing, which is the product recommendation for my people who like that product, also like this one. So this is a real-life data pipeline, and what we call real-life data pipelines have many characteristics. And the first one is that you have a very large diversity of tools and of type of tasks. So there is no single tool, and I really don't think that there will be any single tool able to do all of that. You will use Hadoop for some of them, mostly Pig and Hive. For many of these tasks, you will want to use Python, because Python has excellent support for many data analysis tasks. You might want to use R for statistical processing. So really lots of things. And in a real-life company, all of this will evolve extremely frequently. You will have new steps to add, new data, new processing. You are going to change the way your website works, and you are going to have to change the data pipeline to accommodate that. And due to this large evolutivity, what we call exceptional situations are really the norm. So exceptional situation is really, I've changed my input data for my filtering stuff, and so I need to recompute all the previous data to bootstrap my new algorithm. If I don't recompute, everything will be skewed, etc. Or this day, my tracking provider had a failure, so I didn't get the log, so I will need to reprocess it, etc., etc. And there are many pains associated to all of that, like sharing a schema. You have, as I said, lots of tools. Each one has its own view of what my data is, how it is stored, how the schema is handled, and just that is a mess. And you also want to do some efficient incremental synchronization, incremental computation. Of course, when you were working on tracking logs, you want to only compute your data on today's, or actually yesterday's tracking log. And you want to track clearly the state of each dataset. We think the evolution of all of that is really similar to what we've seen in build systems. Build systems started with shell scripts. You basically just said what you wanted to do. But quite quickly, some things happened, appeared, makefile, and most importantly, a notion of dependencies. So makedeps, it's already 30 years ago that we started to say, oh, if I have already compiled this file, I will check the timestamps and not recompile them. And then, much later, we started to have new tools, so mostly scans, CMake, and Maven in the Java world, where you started to have some more high-level tasks. So you don't, nowadays, you don't anymore say, you don't have to write, okay, to compile this library, I have to compile each file one by one, then call AR to make an archive, then run lib, then strip, etc. You have higher level tasks that are packaged, and you have really better dependency management because the tools are aware of what they are doing. It's not, they don't just execute dumb tasks. So the evolutions that we've seen on build go in the sense of better dependency management and higher level tasks built in, known by the tools. And we think there is the same evolution for data pipeline and big data systems, where when Hadoop was released in 2006, 2007, everybody just wrote shell scripts. Then we started to have some tools like Hadoop Make and Uzi, which provide higher level scheduling. Uzi knows how to run a pig script. It just doesn't run the pig executable. But we think we still can go further and put more intelligence and more dependency management stuff in a data pipeline scheduler. And that's what we are trying to achieve with a tool called Dataiku Flow, which is a data-driven orchestration framework for complex data pipelines. This might sound a bit bullshit. So what do we mean? What do we mean by that? You want to manage data. You don't want to manage steps, tasks. What you want is data. And that's exactly what you have in build systems. You want all the pains that we discussed about, so all the maintenance, rebuild situation being handled natively by the tool. And you want all of the pains, specific pain points of complex data pipelines handled. So basically, Flow is in its concept quite simple. You have one concept, which is simply a dataset. What is a dataset? Simply put, it's like a table. So it has a schema, it has records. And a dataset, an important thing is that it can be partitioned. So partitioning is really semantic split of your dataset. So most often it will be time-based partitioning. You are processing something which is logs, basically. And so you partition by day. But you have also some value partitioning, like partitioning my user data by country, etc. And a dataset is a logical view over any backend, basically. So a backend could be a SQL database, obviously. Many NoSQL stores can be viewed as a dataset. And obviously, a HDFS file or any cloud storage file for processing by Pig, Hive, or MapReduce. And then, now that we have datasets, we need tasks. Simply put, a task is something that has input datasets and that computes new output datasets. And where it's interesting is that the task, the simple fact that we define this task define dependencies between these datasets. The daily aggregation dataset depends on the customer's dataset. And some tasks are built into Flow with a strong integration. We'll see what that means later. But you can also run some quite custom tasks. So just with these two notions, we can create what we call a flow. So a flow is really a graph of datasets and tasks. So that's a simple one to compute sessions and visits statistics for an e-commerce website. And the first distinctive point of Flow is that it's what we call data-oriented. So in many scheduling systems, you manage a DAG of tasks. So the fact that you have a graph of tasks allows you to have dependencies between tasks. And so you know that if that task failed, then I cannot run this task. I have to retry it, or I have an error path, etc. but you still only manage tasks. In Flow, you manage both tasks and datasets, and that's what makes it data-oriented. So the thing is, you are not going to ask, run this task. You are not even going to ask, run this task and then all dependent tasks. What you are interested in is the data. So what you ask is, this dataset, this output dataset, it's what I want. It's the output of my data pipeline, and I want it computed for this particular day, for this particular partition. And then it's the system that will manage what tasks are needed based on the current state of the system and the tasks to go to the output. So you don't execute tasks, you compute datasets. And that is still very similar to what modern build systems do. In scans, for example, you type scans, the name of the output executable that you want to generate. And one important thing in this dependency management stuff is what we call partition-level dependencies. So here is a very simple example. I have some web tracking logs, so really the logs of all actions of my users on my website. And always the first thing that I will do is that I will clean up, I will normalize it, I will enrich it to make it usable. And that makes what I call the clean log dataset. And then I want to make a big aggregation of all visits on the last 7 days to compute sliding statistics. And for that, I decide to use Pig, because Pig is extremely well suited to this kind of tasks. So both my input and middle dataset are partitioned by day. Each day I have the data for this particular day. But the weekly aggregation stuff needs not only the data of the day that it's working on, but also the previous data. And the previous data must be up to date, it must be clean, it must have been verified. And for that, what you do in Flow is that you declare a partition-level dependency between the datasets. So you will say, there is a sliding days kind of dependency between these datasets. And then if I ask Flow, okay, now compute my weekly aggregation for this particular day, it will compute, go back the chain of dependencies, compute that I need a clean log for 25, 24, 23, etc. And keep going back until it reaches the sources, and then use timestamping and checksumming to check, okay, I have already computed clean log 2 days ago, but for some reason the web tracking log has been re-updated since, so I need to recompute it. And it will do all of that automatically, and in parallel, it will do all the web tracking logs, and then, only then, it will do the Pig aggregation. So we have automatic parallelism, because we can compute the global DAG of all activities, and then once we have done that, we are more, it's more like traditional schedulers. You use the graph of datasets and tasks to compute the DAG of what you have to run exactly, and that gives you a list of steps, a list of stages, and where you can parallelize and where you cannot. So in the previous example, all the 7 daily aggregations, daily cleanup tasks, can actually be run in parallel. They have no dependencies between them. But then the final one can only be run when the 7 previous ones all have succeeded. And of course, it's quite simple on such a small example. But when you have a huge pipeline with truly dozens of tasks, you cannot manage all of this parallelism manually anymore. It just becomes quite a mess, and you have to make some shortcuts or not optimize enough. So this dependency management built-in and partition-level dependencies are really the core differentiators that we think Flow has. It has a few additional nice things, we think. The first one we talked about is schema. Datasets have a schema which is expressed in a common language and which can be translated in all the tools for which Flow has a deep integration. And also what we call data validity checks. The idea is that it's very often you can have a task which succeeds. Okay, you run the task, return code is 0, everything is okay, but actually no data has been produced or completely wrong data has been produced. And this is extremely easy to get it wrong, especially with all that looks like logs, so text files where suddenly a column can be messed up. It's extremely easy to get it wrong. And so we want to have data validity checks which are executed automatically. You declare some validation rules, and each time a dataset is refreshed, validation rules are executed. So it can be a check that a given record that I know must be always here is present, or it can be something more clever, like check that from one day to another, there is not a huge variation in the size of the output dataset, because it means that something is off. And we think it's extremely useful because it produces automatic tests for data pipelines. So we all know that in software engineering, automatic tests are good, and there is no reason that it's not the same case for data pipelines. We think Hadoop is a great ecosystem, and Flow has some native integration into Hadoop, and that's mostly when we talk about Hadoop in the context of data analytics, it's mostly Pig and Hive. So we have native knowledge of Pig and Hive schemas, loaders, storage formats, which allows the user to concentrate on writing its algorithm and not just repeating the schema of each dataset. However, as I said earlier, you cannot do everything in Hadoop. So if Hadoop is a first-class citizen, a very important thing is it's not the only citizen, and you can very easily have non-Hadoop tasks in a flow, and you also have deep integration of non-Hadoop tasks. So that means SQL, and that also means synchronization, automatic synchronization from source systems and to output systems. For example, after executing a complex Pig aggregation, you often want to load your data to Vertica, for example, for quick analysis. So you might not need that in the future with Impala, Drill, or Stinger, but for the moment, you can't really use Hive for real-time processing. So I guess the question might come: what about Uzi and H catalog? Oh no, sorry, this Uzi. Uzi, for those who don't know, is a workflow scheduler for Hadoop. It has an extremely nice integration into Hadoop. So with Uzi, you can really simply execute Pig tasks, Hive tasks, MapReduce, and to some extent, some custom tasks. We think we can go further by really putting some notion of dependencies and putting the notion of dataset at the center. And H catalog is a schema management for Hadoop. So it provides a centralized schema. We would like to use H catalog in the long term. For the moment, we have preferred to develop a very small, very simple centralized schema management thing, which we think is more simple, but in the long run, we might want to switch to H catalog. So what is the status? As I said, we just started. So we have the core engine with all the ideas that I exposed up and running, and we are still under active development for having some betas. And we have a small website where you can subscribe to get more information. I guess there will be the question, so I will answer it. Is it open source? As I said, we are an extremely young company, so we are still experimenting, we are still testing models, business models, etc. So nothing is certain yet. Our current plan is to have that as open core, so like actually most of the open source technologies driven by a company, meaning the core engine being open source and some additional modules, additional tasks, additional enterprise stuff being closed source. But we are still young, that might change a bit. So just to make you wait, we have one last thing to show. Have you ever been annoyed by transferring data between systems? Chances that if you are a data scientist in some way or another, you've already used some or most of these tools just to do some data transfers and make data ready to be usable by another system. And we felt that pain and it annoyed us. So we created DCTC, the Dataiku Cloud Transfer Client, which is an extract from Flow, and which allows you to manipulate files across a large number of virtual file systems with very normal and intuitive commands. So you can do reading, writing, copying of data, incremental synchronization, transparent handling of gzipping, ungzipping, zipping, unzipping, etc. Doing some splitting of files, editing remote files directly in your favorite editor. We think the DCTC is really useful, and you can get it right now. It's available on dctc.io, and we'd really like to have some feedback.
All right.
Thank you very much.
Let's thank the speaker.